Now, the second example that I'd like to discuss is the Sierpinski gasket. And this is discussed in section 12.2 of our textbook. Here, instead of starting with a seed and pasting stuff on, we will start again with a seed, but we will carve stuff away from it, as you will soon see. So how do we begin? We begin with a triangle filled in. So let's say blue paint, and it's filled in here. It could be an equilateral triangle, and that's what I'm going to show. That's what I'm showing in my pictures. But in fact, from the discussion in the book, you'll see you can use any triangle at all. Whatever we start with, we'll call it the seed. Now, step one is connect the midpoints of the edges, and you'll see that that creates a smaller triangle. And what you want to do is you want to remove it. Just take it away. So if you think all of this was painted blue, what we're doing is we're erasing or taking away some of that blue. Now, when you've done that, what you can see is, another way to think about this is rather than a big triangle with a little triangle taken away from it, we can think, we've got three smaller filled in triangles. And that's the way we want to think about it to go on to step two. Because in step two, you can almost guess what's coming, can you? We're going to take out a little triangle, an even smaller one from each of those three triangles. Okay? And we're doing that in three places, and we replace each of the small triangles by three even smaller triangles. So now we have 9 even smaller filled-in triangles. All right, now you know what's going to happen. We're going to take out the middle of each of those in the sense that we're going to take out this smaller triangle from each of those blue triangles. And you can see what we have now consists of 27 filled-in triangles arranged in the pattern as shown here. Now we can do that on and on and on. At the next stage, we will have 81 filled-in triangles. And now I'm just going to show you what we get in the limit as well as we can draw it. So you want to continue this process forever. You want to constantly take out this middle triangle from all the solid triangles you have and do that over and over and over again for infinitely many steps. And what you're left with, what you still have after all this throwing away, is called the Sierpinski gasket. Here is again a little movie to show you that construction. I'll let it run through a few times. We begin with the big red triangle, and then we start throwing stuff out, and that's drawn in black. A bit of history. This is named for a Polish mathematician named Wacław Sierpinski, again a figure who bridges the end of the 19th century and on into the 20th century. In fact, he lived until 1969. Sometimes this is also known as the Sierpinski triangle. Let me show you briefly, without saying too much about any of them, some similar constructions. If you start with a square and start removing little squares from inside in the same sort of fashion, you get something that is sometimes called the Sierpinski carpet. Or you can do a three-dimensional version of it, as shown there. You start with a cube, and you start drilling out cubes from inside that cube. For some reason, this one doesn't have Sierpinski's names attached to it, but instead it's called the Menger sponge. And you can also do this construction starting with a pyramid. And here I'm showing a rather crude model. In fact, this is a photograph that I took on my office floor. I just put this model down on the carpet. If I were teaching this class face-to-face, if you actually saw me in the classroom, then I would bring this in. And this is about, about 3 feet high. And I have to very delicately pick it up, and every time that I work with it, it starts to become a little bit more unglued. It's just made of paper folded together, and then it's Scotch tape to put it together. And in fact, when I originally found this model, which I found in an office where I was spending my sabbatical, this was one of 4 pieces. I just took this 4, so you can imagine an even bigger model was made out of this, using this plus 3 extras. Now this one I want to say maybe a bit more about it, although I'm not going to do this in as much detail as the first construction. To get the Sierpinski pyramid, you begin with a pyramid, that is to say a regular tetrahedron. The seed, if you want to picture that here, picture that what you have here is just like a pyramid with 4 faces. There's 1 sitting on the carpet, there's 2 that would be visible to you, and then 1 completely invisible at the back. Okay, that's how you start. Now, step 1, what you do is replace that solid tetrahedron by 4 smaller copies with side length half the original side length. So now we would have 1 sitting on the top. We would have 3 of them sitting on the carpet. Can you picture that? I hope so. Now what you want to do with each of those is again replace each solid tetrahedron by 4 even smaller copies. And then you want to do that again. And then at that point you will have reached step 3, which is actually what the model shows. The model is showing step 3 in the construction. Of course, we want to imagine this carried on, again, forever, always doing that replacement, and therefore having an object that seems to have less and less substance to it as we go along. Now let's return to the Sierpinski gasket. The Sierpinski pyramid may be a little bit hard to analyze as a figure in 3-dimensional space. So let's return to the Sierpinski gasket. And what I want to do here is to think about the area, which you might think of as how much of the color blue do I need to paint it? Well, for the seed, let's say that the area is 1. So just as before, to make our life easy, we're just going to say that the basic unit of measurement is the triangle that we use as the seed. It has area 1, and we'll measure all other areas using this as our unit. Now, at step 1, what did we do? Well, we imagined the big triangle is carved up into 4 smaller triangles, 3 blue ones and a white one, and the white one really is the one that's thrown away. So we only have 3 of the 4, and then we have a figure with area 3/4. At the next stage, we're now going to take each of those smaller triangles, and we're going to throw away a 1/4 of them. So that means that the blue area that we now have is area 3/4 of 3/4. In other words, 3/4 times 3/4, which is 0.5625. At every stage, the area that you're getting is 3/4 of the area you had at the previous stage. So at step 3, the area is 3/4 times 3/4 times 3/4. Which is 0.421875. Well, we want to consider doing this over and over and over again. I've shown you in this table what happens in the first 5 steps, and it's very easy to calculate the total area at each step. All you do is you take the previous area and you multiply by 3/4. Again, you see we're generating a geometric sequence, and because the common ratio, 3/4, is less than 1, this total area is going to 0. We could be fancy and give a formula for the total area at step k, which is 3/4 raised to the kth power. So, for example, if k is 0, we get 1. If k is 1, we get 3/4 itself. If k is 2, we get 0.563, and so on. Since this common ratio 3/4 is less than 0, the total area goes to 0, and so we declare the area of the Sierpinski gasket to be 0. It has no area. Now that may seem a little surprising. We started with something which had an area, and we took stuff away, We're saying what we took away has a total area of 1, what's left has total area 0. And yet obviously it's not empty. Let's go look at the picture way back here, okay? There's still stuff there. There's plenty of stuff, plenty of points. For example, the 3 corners that we started with are still there. They were there at the beginning and they're never thrown away. So there are lots of points there. And yet the area is 0. Well, that shouldn't be totally surprising. We're just asking an area question about somehow the wrong kind of object. If you have a line segment and somebody asks you what is the area, what is your answer going to be? You'll say, oh, the area 0, it's really not truly a two-dimensional object. It has no thickness. When we draw it with a pencil or a pen or something, we need to use some ink or whatever. But in fact, that's only because to draw it, we don't draw the idealized geometric object. We can't draw the idealized geometric object. We know that it has no dimension. It has no width to it. Okay, so that's an example much more familiar of something that has area 0. Also, the Sierpinski gasket, despite the fact that it looks like it fills out some area, in fact has a total area of 0.